Hello students, welcome to week 10 of Programming for Analytics. Today, we're not going to cover as much new material, at least not conceptually. Instead, we're going to look at a different application, or rather a set of tools that implement some of the concepts that we talked about last week. For example, last week we talked about what the general aim of machine learning is, that is, to make predictions on observations we haven't seen yet, and to quantify how right or wrong we are in making those predictions. Last week we went through kind of a manual process of doing that, a very simple way of creating models. We looked at which models are better or worse, just taking the overall mean or taking the within group mean, and we really just stopped there in terms of making models. Of course, there was a lot of information that was still left over in that data set. You'll remember that when we looked at the diamonds data set, the best model that we came up with was really just a model that took the grouped average and made that one of those 5 predictions for every single observation that we had. Most of the information, it would seem, has to do with carat. How big is a diamond? That's the thing that really predicts how costly a diamond is going to be, and we didn't incorporate that all into our predictions. So today we're going to take that same case and we're going to tackle it using Sc-Learn. I said this last week, but Sc-Learn is to machine learning what dplyr is to data analytics. It really is the gold standard set of tools that is very well thought out, that has been developed for many years at this point. And it's basically one of those tools that everyone who is going to build a model is going to use. When you work as a data scientist, if you are already working as a data scientist, or you will be soon, if you're asked to make a prediction model, you will use Sc-Learn, or rather, I hope you do. So that's what we're going to focus on today. We're going to focus on getting you comfortable with a handful of tools that the Sc-Learn library provides that's going to make your modeling job much easier. So why don't we open up a new file? Of course, we're going to do this in a Jupyter notebook. And this time, I want to pip install Sci-Kit Learn. Actually, Sc-Learn, and do it in Python. I don't know if Sc-Learn itself is the name of the library, although I'm pretty sure it is. I think the official name is like Sci-Kit Learn or something like that. Yep. So let's go ahead and let's take a look at pip install Sci-Kit Learn, because I'm pretty sure it's called, here we go, yep. So pip install Sci-Kit Learn. My bad. Looks like I was right the first time around. So let's go ahead and download that and see what we get. Let's take a look at what we're going to cover today. So we're going to talk about what Sci-Kit Learn is, and we're going to talk about pipelines. Now, when we first cover pipelines, I warn you, they're not the most intuitive thing in the world, but once you get your head around them, you really start to see the power of using a pipeline. A pipeline is, think of it as a recipe. It defines the steps that you're going to use to go from your initial data to your model and to make predictions. And so when you change one step at a time, you don't need to go back and redo all of your stuff. You can still just dump your data into the top of the pipeline and you'll get predictions out at the end. So great, looks like we got Sci-Kit Learn. So why don't we go ahead and do import pandas as PD, import numpy as MP from plot9, import star, and we'll import Sc-Learn modules as we need them. So a module is a smaller part of a library that you can call that only has a group of related functions. So for example, we only want to do a limited number of things. One of the things we're going to do today is to normalize our data. And so when we need to scale our data, normalize it, we'll just call that specific function. In R, when we call a library, we basically get R ready to use every single function in that library. That can be a little bit wasteful when it comes to memory. And so instead, we just want to tell Python, hey, just be ready to use this handful of functions. So as we need them, we'll go back and we'll do just that, right? So let me go ahead and let me save this in our lab 10. Call this lab 10. Yep. And let's go ahead and read in our data as we have for the last 3 weeks. Take a look at our data. Good old Diamond's data set, right? So we've talked a little bit about what Sci-Kit is. Sci-Kit is really just a set of tools that we use to build machine learning models that systematizes all of the stuff that we did yesterday. You're going to see me flipping back and forth from my browser to Sci-Kit because frankly, a lot of these functions are not functions that I'm like 100% committed to memory, the way that basically just a basic data munging is. I can basically do any data munging task in R and Python very easily because I do that for 90% of my work at work. 90% of my work is data munging. A much smaller percent of it is using these functions. It's not that I'm not familiar with them, it's just that they're not quite committed to memory. I'm telling you this because I don't want you to feel, for example, ashamed or feel pressured that, oh, I should get to a point where I know how to use all of these functions off the top of my head for 2 reasons. One, the internet and frankly LLMs exist, and it would be silly not to expect you to use them to do your homework, to help you learn to become a better coder. And 2, the fact that I haven't committed them to memory should tell you something about the proportion of your work that you should expect to spend doing model building. Yes, Sci-Kit Learn is an invaluable tool that you need to know how to learn when you're a data scientist. But even as a data scientist, and a data scientist who can choose to do as many modeling projects as I want to, the fact of the matter is most of my work really does come down to analyzing and visualizing data, and a much smaller proportion of my work comes down to explicit modeling. That's not going to be the case in every single job, but you're going to spend a lot less of your time doing modeling. And so don't feel ashamed if you need to pull up documentation. That's what it's there for. So we have our data set, and let's talk about normalization first really quick. One of the things that we did last time is we took a look at the distribution of the price variable, but instead this time I want to take a look at the distribution of our caret variable. Let's take a look at that real quick. So I know my data is in data. I know on my x-axis I just want caret, and I just want to see what the distribution is. So a histogram is good for that. Let's just do that. Let's see what we got here. A lot of variables, of course, so it's going to take a minute. It looks like we have several, or at least 1 or 2 cases that are way out here on 5 for caret. So these are gigantic diamonds. I don't know how much 5 carats is, but I'm guessing it's pretty big. We got this weird kind of distribution. Now, there are technical reasons for this, but we're not going to get into them right now. One of the things that you should know is that machine learning models have a much easier time dealing with data when it looks like a normal distribution. This does not really look like a normal distribution. And in particular, we want our normal distribution to be centered at 0. So if you think of kind of the hump, the classic symmetric hump of a normal distribution, the thickest part of that hump should be at 0. And then what we really want is what's called unit variance. That is, our spreadness is kind of mostly concentrated around the -1 to 1 region. So why don't we, before we even fit a model, we know caret is going to go into that model. So why don't we go ahead and try and implement that so that we can contrast it with how we would do it in Sci-Kit Learn. So we'll call this normalize or standardize or scale the caret variable. So we're going to take caret. Let's take a look. And I want to subtract out the mean of caret. Whoops. I'm going to subtract out the mean. Now you'll notice that there are some negative values now. That's okay. That's all right. What's really important to us, or rather what makes it easier for the model to see, is not really what the absolute value of these numbers is, but rather where's the variation. And the last thing we want to do is we want to divide by the standard deviation. That's it. So why don't we go ahead and put these. First, we wanted to subtract out the mean. Then we wanted to take out the standard deviation. And why don't we put this in a new column that's called normalized, or rather scaled caret. And if we take a look at our data set, we can see scaled caret, right? Okie doke. And why don't we go ahead and plot scaled caret to see what it looks like real quick. On the x-axis, I'm just going to put scaled caret. I'm going to do the same things I did previously. Let's take a look. You'll notice that we didn't really do much to change how spread out these variables are, unfortunately. It seems like our squishing procedure wasn't particularly useful. It's a little bit different. You'll notice, for example, that it's a little bit thicker here, but we haven't really fixed this spread out problem. That's a little bit concerning, but it is what it is, right? It's a little bit more squished, but essentially all we've done is we've taken the bulk of this distribution and we've put it over 0. That's going to help the model, and we'll see that a little bit later. All of this is kind of irrelevant for the sake of actual analysis, right? As you'll notice, these two look very similar, and if you were to put these side by side and ask someone to find the difference, they'd be hard pressed to do that, right? This is a very cumbersome way of accomplishing this. We don't really want to have to do this every time I want to normalize a variable. Instead, I want some systematized way of putting my data in at the top of a pipeline, having the pipeline do its thing, and out comes standardized data, right? So we talked about normalization, and that's what a pipeline does. It puts together different steps. So let's go ahead and tab over to Sci-Kit Learn pipelines, and let's import this module. Let's go back to our library. Let's do that. What are we looking at here? This looks a little bit different than the other ways that we've called libraries, so it's worth taking a minute to explore this. Note that Sci-Kit Learn on its own is an entire package, or library. If I really wanted to, I could just load the entirety of Sci-Kit Learn and we could go from there. But instead, I only want to import one specific function. That's a pipeline function. That's what I'm going to do. Right? So, pipelines put together different steps. And it puts together different steps in a set of sequences. It's going to take your data and it's going to do each of these steps, and then it's going to output whatever happens at the end there. And it takes these as a list of tuples. Tuples are not a data set that we discussed in previous sections, but basically a tuple is an immutable pair of objects, kind of like a dictionary, but you can't change what a tuple is. It may be a little bit easier to show you in practice what this means. So the first thing we're going to do is we're going to name our tuple. This is going to be standardize. The next thing is we're going to tell it what standardize does. So let's take a look at this documentation. So here's a pipeline that they're creating, and they're going to say, do the standard scaler, scale your variables. That's what we want. But you'll notice that standard scaler comes from a different part of the Sci-Kit Learn library. So let's go ahead and load that library while we're at it. The standard scaler does exactly what this is. We scaled our data set. So one of the things I want to do is I want to take my pipeline and I want to use it, and I want to run data in through the top quote unquote, of it, and I want to see what it produces on the bottom end. We know the standard scalar just does what we did here. And so I want to take our standard scalar and I want to be able to verify that that's what it's doing. Now, at this point, the benefits of this are not exactly obvious. It's the same step that we accomplished in about as much code. But as we continue to add steps, the necessity of not having to go back and rewrite all of that code is going to become more and more apparent. So I just want to look at my caret variable, but I need to do a couple of things to it first, and we'll find some functions that will help us do this more smoothly later on. But I need to turn this into a NumPy array first off. Let's take a look at temp. So the pipeline takes NumPy arrays. Now there are other functions to help you do this, but for now, we're going to do that. Let's see what happens when I take my pipeline and I say fit transform temp. It says reshape your data either using this, or if your data has a single feature, or array.reshape1 -1 if it contains a single sample. My data only contains a single feature, so let's go ahead and let's use reshape. And remember, reshape is a method. And let's take a look at what reshape did to our data before we run it through the process. It basically just made every single individual observation into its own little NumPy array, right? That's all it is. For whatever reason, pipelines need this format data. And when we give it the correct format, we get some output. Let's take a look at data and let's see if that lines up. Sure enough, it does. These are all the same variables because it's doing the same thing. In fact, you might say this is a little bit less code that accomplishes something that's a little bit more cumbersome. I'm going to delete this visualization right here. I think you guys kind of get the point, and I think it's a little easier to see these two things together and say this and the above step do the same thing. So we have our standardize, right? But one of the things we notice is we have to do all of this finagling. And going back to last week, we noticed that we did a little bit of train test splitting that we haven't yet done here. So why don't we go ahead and do that? And in fact, if we go back to this documentation, not this documentation, if we go back, you'll notice that there is a function that will help you do this train test split. It'll do it for you. So rather than having to worry about whether or not we dropped the right variables when we randomized our train test split, we can just rely on sklearn to have written or to have a function that is really robust, that's been tested to heck and back, and we know it's going to work. And the less code we have to write, the less error prone that code is going to be. So why don't we take train test split? And train test split asks for two things. It asks for X and it asks for Y. You'll notice when we do train test split here, it asks for X and Y. X and Y are X, uppercase X and lowercase y are our predictors and outcome respectively. So why don't we go ahead and let's split our data set. I'm going to comment this out for a second first, and I'm going to say X is going to be my data set, and all I want right now is caret, and Y is going to be my price. That's it. And if we take a look at X, we get caret, and if we take a look at Y, we get price. Okay, let's go ahead and put that into the train test split, and it needs one more variable, which is test size, which is the fraction of your observations that are going to go into your test set. You'll notice that it spit out 4 different data sets. What's it spitting out here? Well, it's spitting out your feature variables, your independent variables for your train test, your independent variables for your test set, your outcomes for your train set, and your outcomes for your test set. So rather than typing out all this nonsense, because I'm very lazy, I'm just going to copy it. We're going to get that. And why don't we take a look at these objects to see that they are what I think they are? Yep. Great. Okie doke. So here we have it. We don't necessarily need this right now. I'm going to put this here. I'm going to put this here. I'm not too interested in what was going on there anymore because we've systematized this train test split. We have our standardizer. That's terrific, right? It's going to take caret. It's going to normalize it. And then that's it, right? Let's take a look at our pipeline here real quick. It's not doing anything. We haven't fit a model yet. One of the ways that we built a model, let's take a look. What have we done so far? What is a pipeline? Transform. We'll get to error metrics. And let's do what is a model. We'll talk about fit transform a little bit later. So what is a model? In the last section, in the last week, we did a really simple and frankly kind of a silly way to do a model. We just took global means and group by means. But there are better ways of doing those things. You'll notice when we look at that scatter plot from last week that there was clearly a relationship between caret and price. And I'm just going to blow through this real quick so you can see that that is the case. Right? There's clearly a relationship between caret and price. It goes something like a little bit of an exponential curve, but it is what it is, right? Even a line would get you pretty far in predicting this, right? You would predict these smaller diamonds quite well. So it takes in caret, it takes in price, but we didn't use the caret information. Here I want to be able to use the caret information, and I've just put it into the model so far. What I need now is another step, that is my estimator, or rather, why don't I call this my model? And I need to put a model here that can take in caret and use it to make predictions. A good way to do that is through linear regression. So let's take a look at our documentation and see if they use, they don't, they use SVC. And we don't really want to use SVC right now. So why don't we take a look at Sci-Kit Learn linear regression. Regression is a really good first model for you to learn. We could have covered it in R from the perspective of other types of academic research problems, but here all we're really interested in is its ability to make good predictions. Now we'll see if those predictions are better than just taking the average, but here it is. It's telling you sklearn.linearmodel.import linear regression. So why don't we just do that? It's going to be called from Sci-Kit Learn. I think it was linear model import linear regression. Yep, that was right. All we need to do here is then say, okay, I want you to use linear regression to estimate it. That's it. That's how I want you to make your predictions. We had our rule in the previous week, a silly rule, take the average. Now, I want you to use something smarter. I want you to use caret, and I want you to make a continuous prediction depending on caret on how to get there. Clearly, there's a relationship between caret and price. Right? So let's go ahead and pull pipeline up here. What happens now when I say fit X train and Y train? Okie doke. So pipelines struggle when you only have one predictor variable. So we're just going to go ahead and we're going to add another continuous variable, which is depth. Let's go ahead and just add depth. It's rare that you're ever going to have one predictor variable, but for this case, just to make it so that we don't keep running into errors that you're unlikely to run into, we're just going to add another continuous variable. We do it, add another continuous variable, because we want to be able to run it through standard scalar as well. Now, I'm going to take my pipeline, and I'm just going to dump in my same data from above, right? And I'm going to say, take your training data and take your independent variables, caret and depth, and take your outcomes, and I want you to fit a model. By fit, what I mean is I want you to find the best line, since we're using linear regression, I want you to find the best line that you can fit, or in this case a plane, since there are two variables, that you can fit to this data. Make the best guesses you can based on just what you can see. So that's what we've done. Step 1 is it scaled the data. Step 2 is it pumped it into linear regression. And now we can make predictions. So let's take my pipeline, and we're going to say predict X test. And what we get is a series of predictions. Why don't we go ahead and append that onto, or rather, before we do that, because we want to do things the Sci-Kit Learn way in this, we have our predictions, and just like last time, we want to see if they're good or not, right? And we want to do them in a Sci-Kit Learn way. So let's go ahead and let's take a look at what we can do here. You'll notice that it uses score, but this is a classification problem. Instead, what we want is mean squared error. The last time we created an error metric, we used the mean absolute error. Now, that is a metric that's allowed here, but mean squared error and root mean squared error are a lot more common and a lot easier. You'll be a lot more familiar with them because it's a metric that's used a lot more often. So why don't we measure the mean squared error real quick? We'll notice that it's an Sci-Kit Learn metrics and it's called the mean squared error. So let's go ahead and load that in. From Sci-Kit Learn metrics import. Actually, it allows root mean squared error. So we're going to go ahead and we're going to do that. In root mean squared error, so why don't we say predictions are called this, and we're just going to store our predictions in this object. And then I'm going to say root mean squared error. And this function takes two things. What's the true value? We know what that is. That's y in our test set. And we're going to say what were our predictions for the test set? Whoop, predictions. My bad. Here's our root mean squared error. Now, we can try other error metrics as well. Why don't we go back? Why don't we add mean absolute error? That's what we calculated last time from scratch. And it might be a little bit easier to interpret. So we're about 1,000 off on your average observation. Here's a question. Is our standard scalar actually helping? Is it doing anything? Well, why don't we comment it out and let's see. Now we can say MAE for scalar is 1,000. All we have to do is recreate this and see what our error is. And it doesn't seem like it helped very much, right? So in a sense, we don't have to go through all of this rigmarole to get a better outcome, although standardizing is generally a good way to do things, right? So we've done error metrics. Let's talk a little bit about what's happening when we do fit and what happens when we do predict. Sorry, not transform, fit/predict. I've used a metaphor of a recipe, And hopefully, as you start to see what's happening in this pipeline, you can see the distinct steps that go into a recipe. Your pipeline is basically a set of instructions for how to handle and model data. We did basically the simplest version of a pipeline that we can do, but you can imagine any number of other steps that you might want to take to manipulate your data. For example, why aren't we adding a whole bunch of other features, right? Let's take a look at data here for a second. Let's just add all of the continuous variables for a second. So that's table, X, Y, and Z, right? That's it. And our mean absolute error went down by quite a lot, apparently, right? That's like over a 10% improvement, right? So as we add more variables, right? But notice that I didn't have to change anything about my pipeline. The steps that I wanted, the steps to my recipe stayed the same. The Python knows that I want to take all of my continuous variables and I want to scale them. I want to, transform them so that they look roughly normal. And then I want to throw it all into a linear regression model. And then I want to fit. What does fit mean? Fit means take the model and make it as good as you can given the training data. Given the training data. We haven't made any predictions yet. We're just learning as much as we can from the training data. That's what fit does. It kind of creates your model that you're going to use in the next step to make predictions. Once you have fit, you can use that object to predict on cases that you haven't seen. We had to do all of this sort of manually last week by creating means, by creating group means and other things like that. All of this, if I really wanted to, I could put it in one cell, right? I could put it into one cell. I'm not going to do that right now, but suffice it to say, this right here, these 4 cells are essentially a complete template of what all of your data science projects are really going to look like, at least any of them that involve model building. You're going to start with your data. You're going to identify which are your predictor variables and which ones are your outcome variables. You're going to do your train test split. You're going to identify your pipeline. You're going to define your pipeline. What steps are you going to take in manipulating your data? Then you're going to fit the model. You're going to use that model to predict on a set of observations that you haven't seen before. And then you're going to see how good those predictions are. And you're going to try and get this number. Whatever metric you choose is fine, right? There are some that are better for certain situations than others, but you're going to try and get this number as low as possible. The lower you can get it, the better your predictions are. Of course, you need to be careful that those lowering that number isn't just due to random chance like it was last time, but the lower you can get that number, the better. This is it. This is basically the data science workflow. So that's what fit predict does. The last thing is we don't really need to use linear regression here. There are all sorts of different models that we can use. For example, if you look at linear model, why don't we go ahead and look at linear model? And you'll notice that there are a whole lot of other types of models that we can use, like for example, a perceptron, which is the very simplest neural network that we can possibly use. Why don't we see if this can just be dropped in to our pipeline? And why don't we go ahead and load that. So let's drop it into our pipeline. And sure enough, it just works, right? Neural networks are kind of silly in this use case. They don't really add anything and they take forever to train, but we didn't have to basically learn anything about neural networks to be able to use them. We just dropped them into our pipeline and Sci-Kit Learn complied, and it's fitting the model right now. And when it's done, it'll run that, and then we'll be able to see if we can beat 873.5. So that's what, in the Sk-Learn universe, a model is. It is a type of approach that we can just drop in at the end of our pipeline, and it's just a different way of making predictions. Some types of models are better than other types of models. Some types of models clearly take forever to train. If we get to more than a couple of minutes, I'm going to stop this because it's not worth it. So let's go through and let's comment this a little bit. Fit means learn. Predict means make a prediction. Here, we need to calculate how wrong we were to know if we're getting better. This is just nice to have. I'm going to get rid of this for now, and this will be this, right? This is a good template. We don't need this. This is a good template for... I also don't think we need that. There we go. This is a good template for how machine learning projects generally go. This is a very sparse way of doing it, but if you get comfortable with pipelines, and pipelines can get very long and complex, you'll have a good idea of how data science is done in practice. Right? So today we've covered Sk-Learn. We've learned a little bit about how to call specific functions from a package and a module of that package. We read in our data set, we looked at our data set, we did standardization the manual way, and then we learned how to do standardization in the pipeline way. We also did train test splitting, not the manual way. We did it using Sk-Learn, and then we fit and used our model to predict, and then finally we assessed the quality of our predictions. I'm going to stop there for today. At this point, we have basically gotten through all of the super difficult stuff in the class. If you haven't already figured out what you want to do for a final project, now is a good time to really settle down and figure out what it is you want to do. We're not going to be learning anything revolutionary or new in the remainder of this class. Of course, we do still need to cover some odds and ends, but generally speaking, what I hope you do in your final project is to use your data analytics skills, your munging skills, and your visualization skills, and perhaps your newly acquired data science skills, your model fitting skills, to do something that's interesting. Now, interesting means find a data set that is insightful to you on a topic that you care about, and use the tools that you've learned, you've now picked up, to make some inferences about the data that you see. Tell me something about what you've found. So next week, we're going to have much shorter labs. We're just going to go over while loops and recursion for lab 1, and we're going to go over Git and GitHub in lab 2. I may combine these, and you may only just have one lab next week where we just cover odds and ends, but it'll be a much lighter week, and in class, we may do a case study. So, hope you learned a lot. I will, of course, upload this notebook. I'm going to stop this because that's too much. And I'll upload the linear regression version. So practice, do your homework, and I look forward to seeing you all in class.